So basically this is going to be a very brief case study of optimizing memory layout with GHC Haskell. This is the work I did about 2 years ago, and I revisited it recently because I intend to publish it, but I need to make it a bit less horrifying, at least the implementation, in order to make it palatable for the public. So the goal would be implementing closures like radix tree vectors for Haskell. So it's basically some int key sequence with fast random reads and modifies, and fast but not constant time stop, and linear time concatenation. And if you know closure, it's very common to use the vectors in closure. And the basic implementation is, so it's essentially a leafy tree for bit strings, and of course your 64-bit integers can be also interpreted as bit strings. So we have a trie of A, which can be either an empty, or a leaf of A, or a node of a trie of A and a trie of A, but this is not the final version, this is just conceptually the simplest version. And we can do a lookup by iterating over each bit in the key, starting from the most significant bit, and if we have a 0, then we take the left subtree, if we have a 1, then we take the right subtree, and eventually we get down to a leaf. And if you want to make it faster and also a bit more space efficient, we can make the node have a branching factor of either 8 or 16 or 32. In the case of closure it's 32, but in Haskell 16 is much better because we have inline copying for 16 sized arrays but not for 32 sized arrays. But that's a very minor technical detail. So we can try to implement this in Haskell in a naive way. So we might think that we are clever by writing an unpack vector here, but it's actually this is very bad. This is formatted very badly. Okay, but so because the way a vector from the vector library is laid out is we have a vector object which starts with an info pointer, and then we have two integers. One is, because vector is basically, it's not an array, it is a slice pointing to an array. So the first primitive integer is where does the slice start, and the next one is what is the size of the slice. And after that you have a pointer, and the pointer is primitive GHC array, but the primitive GHC array also has an overhead, because it also has an info pointer, and it also has a size. And it has actually two integers for size. Because of garbage collection, you have to have a card table at the very end, and the card table is used for marking mutations in an array in order to do the kind of right barriers in generation of garbage collection. And you don't want to traverse everything in a mutable array if you try to do a generation of garbage collection. So this is a technical detail, but actually the total administrative overhead of a single vector array is 7 words and 1 extra interaction. So if we put this kind of monster inside of our data structure, then we are going to get 7 words of overhead and 1 indirection overhead for every single node. So we can make this slightly better by using small array, which is in GHC since version 7.8, and it was implemented by Joan Tibble, who's the kind of the main implementer of unordered containers. And so basically Joan was very annoyed by array, so he did this kind of small array, and small array is actually really just an info pointer and then the size and then an array. And but if you make small array big, so you can make small array as big as you want, but you get inefficient garbage collection if you try to mutate it. But in the case of data structures, You don't need to mutate it, and you don't need to make it large. So it's completely fine. So it was intended for use in other containers, but actually it's not even used there, even though it was put into GHC for this very reason. Because Johan, I think, kind of retreated from maintaining the library before he get to implement this kind of feature. But maybe maybe I should do a pull request. And so there is only a single integer overhead for restore the class. So, but this is really not what we want. So basically we already know the depth of the overall tree, because this is almost like a fold tree, but it's full to the left, and it may have like for example, if you have a complete binary tree, but you can take a certain path into the tree and make it empty to the right of that path. So I don't know the specific, there is a kind of technical term for this kind of tree, like left complete or left leaning, I don't know. But
I think that exists a well-defined word for that. I searched for such a word for a day and I couldn't find it.
It's like left full or left complete binary tree.
No unique word which everybody acts on.
Yeah. So the point is, we know the depth of the tree just from the size, because we can take a logarithm, and we would also like to compute the logarithm with some kind of bit fiddling native operations, like and we also know whether the next constructor. So if we go down the tree, we know the next constructor, whether the next constructor is leaf or node, because we know at what kind of depth we are, so we can just go down, and if we are at the bottom, we have the 0.3, and the 0.3 is not a tree, but it's an element. So we don't need to have any constructor tags inside our data structure. So we can implement it as a single nested primitive array. So basically as a primitive JC array containing pointers to either primitive JC arrays, or at the very bottom, the elements themselves without any constructor tags. So the revised implementation is like this. So first we import GHC Spring. This is very important because this is going to be our new prelude. And we implement the try as basically a tuple of a size, which is of course an integer, and we will use the size in order to make like efficient safe indexing, and also to compute the depth of the tree with some kind of base fitting operation before adding modify or lookup operation. And the contexts are going to be small array of any. And are you familiar with any? Yeah, so any is basically just like a void pointer. And we need to do this because the type system is not strong enough to conveniently express the fact that we have a tree which is exactly as nested as a given depth. And if we have dependent types, then we can define it as a single type only, but in JC we can't. Or if we try to define it, then we need some kind of hacky ways to emulate dependent types, and that's not going to be fast. So, and then we have something like, so this is just a cutout of a single path through the tree, and we have an inf pointer, then a size, then an array of pointers, but the array of pointers directly point to yet another primitive array. And we have A's in the bottom of the tree. And the GHC runtime system can handle this fine because every object is still tagged with the right info pointer. So garbage collector can follow through this data structure. So there are some kind of technical points of making this work without having segfaults. For example, what happens if you try to force or evaluate a primitive array? You get a runtime system exception, which is not the same as IO exception because the runtime system exception is thrown by the runtime system and is not recoverable. The Haskell cannot even see it. It just, your program crashes with a very exotic message. So what we gain is less than half of the number of indirections to every element, very low space overhead, maybe 1.15 words per element, and you can compare that to exactly 1 word overhead per element for a completely flat array. So it's almost the same as a completely flat array. And the speed is, okay, so I don't have benchmarks, maybe I can show you, but it's not in a very nice format. And I also have to update the benchmarks because I had hundreds of benchmarks 2 years ago, but some of them are now broken because criterion is not the same. So basically we have about 20 to 30 times faster lookup than data sequence, and about 5 times faster lookup than data hash map. And you might ask, why am I comparing this to data hash map? Because data hash map is a general purpose associated data structure and not just key by integer. But I still think I can compare because the hash function on integer keys for data.hash map is an identity function. So in the case of integers, data.hash map as a data structure degenerates or specializes into just an integer trie data structure because it is implemented as hash array mapped trie. But if your hash function is identity, then all you have is just an integer trie. So the modification is about 2 to 3 times faster than data.sequence and about 1.5 to 2 times faster than data.hash map. And so basically there's a bunch of to-dos like make a proper library about this and make internals less horrifying. And so it would be really nice to have an abstraction for having nested primitive arrays like this and a safe API, but it's not yet there. So it's very, very unsafe. And actually we can use the same trick with nested primitive arrays to implement data.hash map, and it would be very nice because it's a general purpose associative data structure. And I believe that we could make it faster using the same trick. And yeah, there should be. I would really like to have libraries in Haskell with minimal space overhead. Because you really need to have libraries for data structure with minimal space overhead if you try to compose data structures from other data structures. Like for example, vector in Haskell is not a vector, it's a slice. Array is a slice from data.array. Text is a slice from data.text. But sometimes we would really like to have space efficient UTF-8 byte strings with minimal overhead, but there is no library that I am aware of for exactly that kind of thing. So I think it would be nicer to have the basic data structure with minimal overhead and then wrappers for slices on the top of those data structures and generic APIs which you can use both for slices and both for the basic data structures. I mean, that's my opinion. And it would be nice to have those kind of libraries. Okay, this is roughly.
Okay.
Yeah.
Any questions?
Yeah. Have you benchmarked against inline or vector?
I can show you. So benchmarking is really hard in general, and you have to do a lot of work in order to make it right, correct? So what I currently do is just have random indices for each size and do basically 100 operations on random indices for each benchmarking batch of criterion batch. So for example, for lookup operations, if I have like a 1,000 size tree or sequence, and I generate 100 random indices, and then I do 100 random lookups for each session of criterion benchmarking. Yeah, basically, and then I do it for a large number of different sizes. For example, like I have this large HTML file generated from criterion for a large number of sizes, and yeah, but it's not very nicely formatted because I should transpose this actually in order to make it more informative. Yeah.
I think I'm not entirely familiar with it as well, but I think Foundation is a new prelude that is being, or prelude or a sort of core infrastructure library for Haskell developed by Vincent Pankes and a number of others. And that has a new string type, which I think is a UTF-8 packed representation.
Okay.
So
Okay, that's very good.
might want to have a look. I don't know exactly what representation they're using.
Yes, okay, but so what I would like to have is a data structured API which is generic over the actual 3 different kind of data representation which we have in Haskell. So the 3 different kind of data representations we have is we have the boxed objects, which are the usual Haskell object. We have the unboxed objects, which we have, but we also have a third category, which are the unlifted objects, which are things like primitive arrays, and also like primitive references like mutrefs. Mutrefs are essentially single element arrays, and those are unlifted. And currently in Haskell libraries, you can sometimes get like a generic API for unboxed objects, but you almost never get generic API for unlifted objects. And I think that that would be also kind of important. For example, if you have an array of strings, if you have like the pegged UTF-8 string, then if you have an array, then you would like to have an array containing pointers to the data directly. Or if you have an array of strings, then pointer to pointer to data directly. And you can have that if you have a generic treatment of unlifted data types. But if you don't have that kind of treatment of unlifted data types, then you have to introduce the boxing and essentially have twice as many indirections. Because you have to treat unlifted objects as boxed objects and have to box them. So, yeah.
Okay, any other questions? No, then thank you.